Hello, once again. Welcome back. Mr. Wakefield here. We're looking at the last section, or at least the last section that we're going to be doing in Chapter 3. I think there's a few other sections in the textbook in Chapter 3 after this section, but we're not going to do those. So this is the last part of Chapter 3 right here. And it is very similar to 3.1, where we're going to be solving systems of equations again. Back in 3.1, what did we have, you guys? We had two equations, and they each had two variables in them. The difference now is we now have what? We now have something a lot bigger. We have three equations and they have three variables total in them. Sometimes you'll see a missing variable in one of the equations, like right here, the second equation. But overall, there's three total variables in the whole problem altogether, x, y, and z. So because of that, we're normally going to get what? Remember back with these problems, because we had x and y, our answer was x comma y, right? The x and then the y. Well, because we now have x, y, and z, instead of calling it an ordered pair like we did in 3.1, we're now going to call it an ordered triple, where you're going to have an x, a y, and a z all together as a group, and that becomes your answer. And just like in 3.1, those whatever those three numbers end up being, they are the three numbers that when you plug them into the x, y, and z respectively, they are the numbers that are going to make all three of these equations true. Remember, when you solve a system, you're finding the answer that is a solution to all three equations. Okay, that means that if you plug it into all three equations are true. All right. The way we're going to do this here is through elimination. We're not going to do substitution. We're going to do elimination. You'll find that that's a lot easier this time. But the answers that you could potentially get are very similar. In fact, they're identical pretty much to what we had in 3.1. It's either going to be one solution, and this time the one solution will look like that because you have the three variables. Or you could have no solution. Or you could have an infinite number of solutions. The one difference also is that when you get an infinite number of solutions, you don't have to write those fancy brackets that we did in 3.1. Remember these right here? Okay, you don't have to write those when there's three variables, okay? It's just too complicated of a thing to describe exactly what the infinite number of solutions looks like when you got three variables. It's just a more complicated problem. So because of that, you are allowed, when we do get an infinite number of solutions, and it'll be the same thing as it was before. It'll be one of those things where you're solving and you get an equation where the variables disappear, but it'll be a true statement. Okay, and I mentioned that here in this part A right here in the current section. When that happens, no variables, we get something like 3 equal to 3 or 0 equal to 0, which means it's true. Then all you have to say is your answer is infinite number of solutions. Okay. Whereas, and again, this is the same as before, when the variables disappear in an equation that you get, and you get a false statement like these two equations are false, then once again, that'll be no solution. But usually you will get a single answer for x, a single answer for y, and a single answer for z. And so we'll just put that together, and then that would then be our final answer. So that's what the answers are going to look like. Now, how do we go about finding these answers? Very, very important you follow these directions very carefully here, okay? And so let's go through them carefully. If you divert from them even slightly, all of a sudden your answer could go in a wild different direction. I mean, we should follow the directions anyway, but I'm just saying it's especially important here. Now remember, we got three equations this time, so it's going to be definitely a different type of thing than it was with the two equations. Just listen carefully here. It says choose a pair of equations. It could be either the first and the second, the first and the third, or the second and the third. Right? Any pair you want in the first step here. And then it says use the elimination method to produce an equation with the variable eliminated. Just like we did in 3.1 when we were using the elimination method, what did we do? The purpose was to try to cancel out one of the variables, right? And sometimes both variables cancel out. Okay, don't panic if that happens. All right, that just sometimes happens. But the goal under normal circumstances is just to try to eliminate one of them, one of the variables. And so that's going to be our goal here in the first step. Okay, now we got a lot of choices here because not only are we allowed to pick any pair we want, but just like back in 3.1, we can eliminate any variable we want. And so it's because we have all these choices, what we want to do is pick something that, again, is the easiest thing to do since you got so many options. Notice here, for example, and we saw something like this similar to back in 3.1. Where remember back in 3.1, the first problem we did in elimination method, we had the x and the 5x. And so I multiplied by -5 right there and then added them together and it canceled. Kind of the same thing here. See how x and 3x are such that if I multiplied this one by -3 right here, it would then cancel with the 3, wouldn't it? Okay, and I'm going to go ahead and write this down just so it's clear, completely clear to everybody what I'm doing. It's not as big of a deal to do this, to write this down when you're doing 2 equations, just because it's a much smaller problem. But just so everybody can see what's going on, I'm going to do -3 times equation 3. I'll call it E3 for short. And then after I'm done multiplying that, I am then going to add it to the second equation. Okay, so that the -3x and the 3x will cancel. Let's see how that comes out. Now, and by the way, the second equation, the one in the middle here, that one's going to stay the same because we want it to be 3x. We want 3x to be there so it'll cancel. So I'm going to keep that the same. It doesn't matter which one you write on top and which one on the bottom. You can keep the third equation underneath. But I need to multiply this one by -3 right here. Remember, as we said in 3.1, when you multiply an equation by something, as long as it's a polynomial on both sides, and we have 3 terms here and 1 term here, they're both polynomials, you just distribute the -3 to all of the terms, and then you keep the equal sign in the same spot. So what would that become? That would become -3 times 1x would be -3x. -3 times -2y would be +6y. Okay, and you got to put, when you distribute, remember you got to put the pluses or minuses in front of each answer. Then we got -3 times 3x is -9x. Okay, and then equal sign stays in the same place, and then on the other side you just got -18. What happens when I now add these together? These cancel, don't they? And we're left with what? If we add the rest of it together, we get 3y minus 10z. I'm just doing the same thing I did in 3.1. I'm combining like terms on the variable side, and I'm just adding these constant terms together on the other side. The problems will probably already have the x's and the y's and the z's and the constants all lined up. If they don't, go ahead and line them up, move the terms around, but it should already be done, so I wouldn't worry about that. Okay. Anyway, add the 2 sides of the equal sign together. We get this right here. That right there, you guys, is step 1. Step 2. This is very important that you observe the 2 words that I underline here. Again, the problem will get totally messed up if you don't keep track of these 2 words right here. It says choose a different pair. You cannot choose the same pair. Okay, so since I chose the second and third equation in the first step, I either need to choose the first and the second or the first and the third. You just can't do the second and the third again. So choose a different pair. And then you use elimination method again, but this time you eliminate the same variable again. So that means what? That means that I need to eliminate x again because I eliminated x from the first step. So let's keep that in mind. We're going to eliminate x. And when we eliminate x, we have to do it either from what? Either from the first and the second or the first and the third. Now, you could do either one. Okay, it's your choice. Just so long as you don't pick the second and the third. I'm going to pick the first and the third just because in that case you don't need to multiply. Like, for example, if I had picked the first and the second, I would have had to do that thing where I had to multiply both equations, where I flipped the 3 and the 2 like I did in section 3.1 and then change the sign of one of those. in order to get these things to be opposites. And again, if you really want to do that, go ahead. It's not a problem. I'm just saying it's a little bit easier to do the first and the third because then you only have to multiply this one by -2, correct? And then that would cancel with the 2x, wouldn't it? So I'm going to do that. I'm going to say -2 times the third equation. And I'm going to multiply, or pardon me, after I'm done multiplying by -2, I'm going to add that to the first equation. And that will make the x's eliminate again, like they're supposed to. The same variable's got to eliminate in each of the first two steps. Now remember, I'm going to keep the that first equation the same right there. Okay, I'm going to multiply the third one by -2. So let's distribute the -2 through all these terms right here like we normally would. That would give me -2x. Plus 4y, right? -2 times -2. Minus 6z. And finally, -12. Okay. Cancel those out. Because when we add them together, they will cancel out since they are opposite sign. Got to be opposite sign. Same number, but opposite sign, 2 and -2. And so that's why the x's cancel. Okay, so notice it produced another equation here which has x eliminated again. And so here's the thing. What you do is you now take those two equations, and I'm going to bring them together in a group here. In fact, I'm going to create a brand new system. This is step 3. But you take those two resulting equations that you got underneath the big lines right here where you added the two equations together, and you make a brand new system out of that. I know it's got different variables than it did back in 3.1. 3.1 we always had x and y, but that's okay. As long as it's the same two variables, it doesn't matter what letters they are. The method still works just the same as it did in 3.1. Okay, so there you go. And so what do we do with that? Well, step 3 tells us to take those two resulting equations right there and actually solve them using the 3.1 method. The 3.1 method. And so let's go ahead and do that. Okay. And again, because we can use the 3.1 methods to do this, you could do either substitution or elimination on this step. On the first two steps, you want to do elimination for sure. Here you could do either substitution or elimination in order to solve this. But it's very important that you solve for both y and z first before you go on and do anything with any of the other equations outside of this. In other words, when you solve this, you're only supposed to deal with equations in here. Okay, so remember like when we did, let me show you what I mean. I'm going to do the elimination method here. Remember when we did the elimination method in 3.1, there was a lot of times where you had to, there were, not a lot of times, but there were instances where you had to plug stuff into another equation, right? Well, when you do that in the current problem, you only plug stuff back into equations that are in step 3. You don't plug into any of these equations over here, any of the original equations. When you're in step 3, you stay in step 3. It's like you're locked inside of a room and you're only allowed to deal with the equations inside of that step 3 room, so to speak, okay? You don't go outside of that and plug stuff into any of these out here, okay? Let's keep that in mind. Eventually we'll get to step 4, and that's when some of these other equations will come back into play again, but not in step 3. So it looks like substitution is not a good idea here. I usually do elimination method on all these anyway, but I'm just saying in step 3 you could do substitution to solve this brand new system if you really wanted to. Now, because I'm going to do elimination, and because 10 and 8 and 3 and 5 are not easy to eliminate by just multiplying by one equation, we need to, again, do what we did here, which is to flip the coefficients of whichever variable you want to solve and then change the sign of one of them. Okay, we're going to do that same thing here. Again, it's your choice of which variable you want to do, just like it was back in 3.1. Okay, so I'm going to go ahead and eliminate y just to pick something. And so I'm going to flip the 3 and the 5. And then I'm going to change the sign of just one of those numbers. I'll make it -5 and keeping 3 the same. So I'm going to multiply the first one by -5, distribute it through, -15y plus 50z is equal to 65. You can see I distributed -5 through there. You multiply +3 by these 3 terms, and what do I get? I get 15y minus 24z, -39. And then as we did in the elimination method previously, we then add the equations together. This is going to become 26z equal to 26. Okay. And then what do we do in the elimination method after? And I'm talking about the elimination method in 3.1, the one where you start out with just 2 variables. You cancel one of them. You now have only one variable left, and so you solve that equation. That's what we did. And we end up with z equal to 1. What did we do after that? We went back and plugged it into any equation that had, and again, we're just staying in step 3 right here until we have solved for both variables in step 3. We are staying in there. You are not going to plug in, as I said a minute ago, you are not going to plug 1 into any of these equations over here. Okay, you got to pick one of these ones here. All right, that's inside of step 3. But that's what we did in the elimination method in 3.1 when we had just the 2 equations, or pardon me, the 2 equations and the 2 variables, is we just plugged it into any equation that had both of the variables in it for that system that we're solving in step 3. So I'll go ahead and pick this one just to pick something. But it's got to be an equation with that comes from step 3 here, and it has both of the variables in it, y and z. So I get 3y minus 10 times 1 is equal to -13. Remember, this is negative. This is plus -10 times 1. So when I figure out what this term is equal to right here, that is going to be plus -10 times 1 is plus -10, which is the same thing as -10. I then add the 10 over to the other side and divide out the 3. If I add the 10 over, I get -13 plus 10 is -3. I then divide out the 3 and I get y is equal to -1. Okay, so I did it. I figured out what both of the variables were equal to in step 3. When you have figured out what both of the variables are equal to, okay, both, in this case, both y and z. It won't always be y and z, but whatever the 2 variables are in step 3, after you figure out both of those, then and only then, not before that, you are allowed to move on to step 4. Step 4 says this. It says, in fact, let me read it to you. It says, substitute the values of the 2 variables you know, in other words, y and z, into one of the original equations. But it has to be one of the ones that has the still unknown variable. What's the one variable that's still unknown? In other words, what's the one variable I haven't solved yet? Well, I've done y and z, so I still need to figure out x, right? Okay. So since all 3 of these equations have x in it, all 3 of the original equations, you are allowed to pick any one of those. As long as it's one of the original equations and it has that variable in it that you're still trying to figure out, that's fine. I'll go ahead and pick the last one here, okay, but you could pick any one of the 3. It'll give you the same answer, okay. And if it doesn't give you the same answer, that means you did something wrong before that threw things off. But assuming you did all your math correctly, it should all come out the same, no matter which equation you pick. Okay, remember this, the coefficient here was 1, so this right here, and this is similar to what we've done before. When you plug a number into a polynomial, okay, you went to solve that equation, which is what we're going to do now, you want to figure out what the terms are equal to that you plugged into. For the first time, we've actually plugged into two different terms. So just figure out what both of those are at the same time. This is plus 1 times negative 1 because it is plus 1 times y. So plus 1 times negative 1 would be plus negative 1, of course. But we know that plus negative 1 is the same thing as just saying minus 1. Plus negative 2 times 1 is plus negative 2. Same thing as minus 2. Okay, and then after you do that, then you go through the normal process of solving the equation. There's no parentheses to distribute out, but we do have some like terms right there. Negative 1 minus 2 is negative 3. We then move over the negative 3 by adding it over. Negative 1 plus 3 is 2. And then finally you divide out the 2 there and you get x is equal to 1. So the final answer, now that I have all three variables, you guys, the final answer is, and I'm going to write it in that same order, x comma y comma z, 1, negative 1, 1. X equal to 1, y equal to negative 1, z equal to positive 1. Okay? And there you go. And let's see another. Obviously, a lot of stuff's going on there, so we need some more practice, and we're certainly going to get some more practice here. This next problem is going to be very similar. The one big difference is that there's a variable missing from the second equation, right? And that's actually really good news as far as time is concerned, which is always nice because these problems are kind of long, aren't they? Okay, well, this one's going to be a little bit shorter because here's the thing. Remember, you guys, we're trying to eliminate a variable in the first step of the problem. We saw that here. And then you're trying to eliminate the same variable in the second step, right? Well, since a variable has already been eliminated, it's not even there, from the second equation, you are allowed to use that as your step 1 result. You can say that y minus 4z equal to negative 16 is your result of one of your first two steps, because the goal in the first two steps is to eliminate one of the three variables. So you're allowed to use that and not have to do any work there. But what you need to remember, though, okay, is that in the other step there, just like we said here, you have to choose a different pair of equations. Now, that doesn't really make sense here, but I'll explain that. Don't worry. We didn't really do the first step, so you can't choose a different pair. But I'll explain that. But you do need to eliminate the same variable, though. So we need to eliminate x because x is eliminated here. Now, when you choose the pair of equations, if you had one of these things where the variable was already eliminated, and you use that as your step 1 equation, you have to pick the other two equations. There's no other choice. You have to pick the other two equations to be your two equations that you use in step 2 in order to eliminate the same variable x again. Okay, I'll explain that here in a second, but how would I eliminate the x's here? Wouldn't I multiply the first equation by negative 3 and then keep the third equation the same? Because then that would give me negative 3x and 3x. Okay. As I'm doing that there, and I'm going to distribute out the negative 3 across the top here, but as I'm doing that, I want you to notice that the reason why you had to choose those two equations instead of picking another pair is that in order to eliminate a variable, you guys, you got to have two things that cancel each other out. So that's why you couldn't pick the second equation there. It had to be the first and the third. You couldn't pick the second and the third. You couldn't pick the first and the third, okay, because you couldn't pick an equation that did not have the variable in it. Both equations have to have a variable in it so that they can cancel with each other, okay? No way you can cancel if one of them is already missing that variable already, because then there's nothing to match up with the other equation so that they can cancel each other. So that's why you had to pick the first and the third. Okay? You can't pick a variable. Pardon me, let me say that again. If you want to eliminate a particular variable, you have to pick equations, both equations that actually have that variable in it. That's the point. Okay, so let's go ahead and add these together. There we go. There we go. All right. And so that's the first two steps then. Again, made easier by the fact that the first step was already done for us. Okay. All right. Now that the first two steps are done, again, just like in the last problem, we take those two results where the same variable is eliminated. What are those two results? Y minus 4z equal to negative 16. And the other one was negative 11y minus 6z is equal to negative 24. Okay, and just like we did over here in step 3 in the previous problem, we now solve for both y and z right here. Okay, using what we learned in section 3.1 when we had only two variables in that section. What would you do to, and remember, you could do either y or z here. Just like in 3.1, you could have picked either one of the two variables that you had. Okay, same thing. Can't I multiply the first equation by 11 right there? And then that would then cancel with the negative 11y here. In fact, I didn't need to draw that line there. We're not going to be adding yet until I multiply first. But I get what here? I get 11y in the first equation minus 44z is equal to negative 176. Okay. And then that adds together with the other one, which I'm going to keep the same because I now have 11y and negative 11y, and that's what I want. I want a variable where the numbers are opposites of each other. And so, no, we don't want to change the negative 11y then. We got what we want, which is for those things to be opposites of each other. Adding these together, just like normal, I get this right here. I then solve that equation, just like in 3.1, and I get 200 divided by 50 is 4, and it's going to be positive 4 because it's negative divided by negative. Okay. And then what did we learn again once we solved one of the two variables in section 3.1? We go back and plug it into any equation from step 3, though, only step 3, that has both variables in it from step 3. In other words, pick any one of these 4 equations because those are the ones that have the two variables in it from step 3, which is y and z. I'll go ahead and pick this one. Looks like it's the easiest one. Y minus 4 times 4 is negative 16. Figure out what that term is equal to that you plugged into first. And we got that right there. Plus negative 16, same thing as minus 16. And that's going to be what here? That's going to be, if I add the 16 over, I'm going to get y equal to 0. What's that last step, though, that we learned in the last problem? Once you figure out what both of the variables are equal to from step 3, y and z, you then take those two numbers and you plug it back into any equation that has the still unknown variable in it. So don't plug them into here. It wouldn't make sense to plug it into here, would it? Because we're still trying to figure out what x is, right? We know y and z, but we still got to figure out x. And so don't plug it into here. You ain't going to figure out x because it's not there. So that's why we're saying plug it into an equation that has the still unknown variable in it, but plug it into one of the original equations. Okay? So we got x plus, I'm going to pick the first equation there, x plus 3 times 0 plus 5 times 4. I plugged in at y equal to 0 and z equal to 4. Okay? And that's equal to 20. Figure out what the terms are equal to that you plugged into, just like we've been talking about. And we get x plus 0 plus 20 equal to 20. Combine like terms. Okay. So when we move the 20 over, we get 20 minus 20 is 0. Okay, so now we know all three variables. Final answer, x equal to 0, y equal to 0, z equal to 4. 0, 0, 4. Okay, so that is the basic idea of how you solve one of these three variable, three equation systems, assuming that you're actually getting a single answer for x, y, and z, which you usually will. But as I mentioned, and we saw this in 3.1, sometimes the variables will disappear. I'm going to show you an example of that right now so that we can get, again, familiar with that as well. Number or problem C on the second page here of section 3.3. Let's go ahead and start doing the normal thing here. Just to be different here, you guys, you don't have to do this, but let's say I wanted to eliminate y this time instead of x, just to be different. Okay, and I said, okay, if I multiply the, here's step one. It looks like I can multiply, you're thinking this to yourself, it looks like I can multiply equation 2 times 2, that would make this negative 4 in the middle, and then that would cancel with the positive 4 up here. So again, it doesn't always have to be x's, okay? Usually I like to do x's, but I just want to emphasize by doing it this way that, yeah, you could pick a different variable. So anyway, let me do this here. 2 times the second equation is going to be 2x. Actually, let me write the other equation first. I usually do that. You don't have, like I said, it doesn't matter what order you write it in. But I'll put since it's the equation that's on top up at the beginning of the problem, I'll keep it on top. It's just easier to follow that way. And then the second equation, when you multiply by 2, it becomes 2x minus 4y plus 6z and then negative 12. Okay, let's see what happens when I add those together now. I get the y's cancel, and I get 5x plus 11z. It's okay to have that gap right there, all right? Just so long as when you combine like terms, you got to have, again, pluses or minuses in between the terms in front of each term, okay? As long as it's in between 5x and 11z, that plus sign right there, because 11's got to be positive, that's what's important. You can have a gap there still. Step 2. Since I eliminated y from the first step, I have to eliminate y again. And I have to pick a different pair. Okay? So I have to pick, I could do, oh, hey, check this out. I could actually add these two equations together here without even multiplying by anything, right? Okay. Why don't we do that? Okay. There we go. And so that happens sometimes. Sometimes it's already set up to where it cancels without multiplying. What do we get here? 5x plus 11z equal to 16. Okay, so what do we do, you guys, after we find our two equations from the first two steps? We put them together as a group into step 3. Here we go. Just bringing them over here. Notice that they both have the same two variables, x and z on both of them, right? That is very important, that they both have to have the same variable in step 3. And that's why you always eliminate the same variable from each of the first two steps. Okay? The other two variables will then be the only two things left over. It looks like I can do elimination method here again. If I multiply, say, this equation by -1 right here, okay, like this, and then add it to the other equation, I would get 5x being added to -5x. That's what we want, right? So I keep the first equation the same there. Multiply the other one by -1, and I'm going to get this right here, -5x minus 11z. Remember, when you multiply by -1, all it does is change the sign. The 1's not going to do anything. The negative changes signs, though, of what you're multiplying. Look at what happens here, though, and we saw this in 3.1 also. Everything cancels when you add these two things together here, when you combine like terms. And that would be equal to 0, as we learned back in 3.1. When everything cancels and when you're combining like terms, it's just equal to 0. This is equal to negative 20, though. What does that mean when the variables go away while you're in the process of solving a system? If you get an equation where the variables completely go away, but it's a false statement. In other words, 0 and negative 20 are truly not equal to each other. That's a false statement. That means what? No solution. Again, you guys, if this had been 0 equal to 0 or negative 20 equal to negative 20, that's different. That would be variables disappearing with a true statement. Then it would be the infinite number of solutions thing. And again, like I said, when you got the three variables, you just have to say infinite number of solutions. No fancy brackets are needed. I'm mentioning this because one of these three problems that I'm about ready to ask you to do right here, it's going to come out like that. No variables, but it'll be a true statement this time, so watch out for that. The other two equations will just be the normal, the other two systems will just be the normal thing where you'll get 1x, 1y, and 1z. So go ahead and please try that. Okay, it's going to take you a little bit of time here, more than normal, but go ahead and try that, and let's see how it turns out. Remember, when I show you the answers, my answers might look a little bit different because remember, there's all these different choices that you have. Okay, but if you do it correctly, following the directions I gave you, it should come out the same as mine in the end. All right, it's okay to choose a different variable to eliminate it first than I did. It's okay to choose different pairs of equations, all right, than I did. Just so long as it's not one of those problems where there's a variable missing. Okay, if there is, remember when there's a variable missing, what do you do here? I'll just get you started here. What do you do here when the variable is missing? You make the one where the variable is missing, you make that your step 1 result. And then in the step 2 result, you have to then pick the other two equations to eliminate the same variable, which would be y. Y was eliminated here. Therefore, you need to pick these two equations to eliminate y again. Remember, both equations have to have that variable in it if you're trying to eliminate that variable. Okay. But when all three equations have all three variables in it and there's no missing variables, then you got all kinds of options. And that's what I'm saying here. But if you do it right, you should be fine. Now, a couple other things here. First of all, there are so many multiplications and additions and subtractions going on in these problems. Okay, all it takes, you guys, is to make one little mistake, and then all of a sudden, you don't have to write this down. This is just an example. This happens to a lot of students. All they do is make one little tiny arithmetic mistake, okay? They accidentally say 2 plus 2 equal to 5 or 6 plus 4 equal to 9, something like that, okay? All of a sudden, that causes the problem to completely go haywire, and you end up getting a crazy-looking answer like this. I'm just making this up here. I promise you, though, right now, and that's why, first of all, I want to encourage you to be careful with your multiplication and addition, subtraction, and all that. Be really careful, even more than normal, so that this kind of thing doesn't happen. And I say that not because this is something that you don't ever see as an answer, but I will promise you, in this section, when you get the three variable, three equation systems, I promise you that the answers will always be either, and I'm talking about all three variables, x, y, and z, the answers will always be either a whole number or negative whole number. You won't get any fraction answers or decimal answers. It'll be nice whole numbers like ones, or negative whole numbers like -1 or 004. Again, these are all whole numbers and negative whole numbers. Okay, no fractions or decimals like this crazy thing here. Okay, so if you do get a crazy answer like this, where it's a fraction and it doesn't divide evenly into a whole number, okay, then that means you did something wrong, I guarantee you. And so that'll be a nice hint for you to go back and try to fix that, okay, and go through all your steps and find out, because the mistake could have happened on any step, so you got to go through all your previous steps, okay, and nobody wants to do that, right? But at least you would know that at least you would know there was a mistake. It'd be no fun trying to find it, but at least you know. But that's also motivation for you guys to be really careful to begin with throughout the problem, to not make any mistakes. So be extra focused on your multiplications, your additions, your subtractions, so that you don't end up with one of those crazy answers. Okay? So I wanted to let you know that. All right. But please try those 3 problems. Hit the play button when you're done. We'll see how it turns out. And we'll wrap up this chapter. All right, let's take a look at number 1 here. I decided, and again, we got a lot of choices here, but I decided to eliminate the x's from the first and second equation here by multiplying the first one by -3, so that I would get what? So that I would get -3x and +3x. All right, again, you didn't have to do that. You could have eliminated the y's here. In fact, you could have done that without even multiplying, right? But it was just a choice that I made. I got what? I got 4y minus 11z equal to -26. Okay, so that's step 1. But since I did eliminate the x's from the first step, I have to what? I have to eliminate the x's from the second step too, don't I? And so I picked equation 1 and equations 2 in the first step, so I got to pick a different pair. I went ahead and picked the first and the third. Okay. So let's see how that turns out. Since I picked the first and the third, I multiplied the first one by -2, so that I would have -2x and +2x, like this. Okay. Remember to multiply all the way through the equation. All right, in this case, -2 gets multiplied by all 4 terms here. Then add the equations together. The x's again cancel as they're supposed to, and we get this equation down here. What does all that mean? It means that I take those 2 equations that I just found, okay, this one here and this one here, and I bring them up to here. Okay, and then I solve that system, just like we've been doing. I went ahead and I flipped the 4 and the 6. It's really the only way you can do it, unless you want to flip the 11 and the 5. You can't just multiply by one equation only this time. Okay, unless you want to get fractions. Okay. So doing that, I get these 2 equations here, multiplying by -6 and 4. All right, and then when I add those 2 equations together, I get this right here. If I then solve that equation by dividing both sides by 46 to get the z by itself, I get z equal to 2. Yes, it's a whole number. It always will be if you do it right, I promise you. Okay, at least the problems I give you anyway. I then need to solve for the other variable in this step 3 situation, which is y. And so that means I go back and plug it into any equation in step 3 that has both variables in it. Remember, it's got to have both variables in it so you can solve for the other variable, just like we've learned in 3.1, okay, when you got the 2 variable systems that you're solving. So I plug it into I decided to pick the second one up here, plug the 2 into there, and I get 6y minus 10 equal to -16. I go ahead and solve that resulting equation, and move over the 10, I get -6. And finally, I divide out the +6, and I get y equal to -1. We're almost there. Okay. Last step is step 4, where you have to go back to one of the original equations, and you pick any equation that has the variable in it that you're still trying to solve, which is x. Well, all 3 of them have x in it, so take your pick. Okay, it could be any one of those. I went ahead and picked the very first one there. As you can see, I made an arrow for that. Plug -1 and 2 into their respective spots there. -1 plus -1 times -1 is plus +1. And then the +6, as you can see right here. Combine like terms, move the 7 over. And final answer there for the x part anyway is going to be x equal to 1. Okay. So putting all 3 of my answers together, I get X equal to 1, Y equal to -1, Z equal to 2. And that's number 1 right there. Again, all three answers are what? All three answers are whole numbers or negative whole numbers, okay? These problems are long enough without having to deal with fractions or decimals. That's another reason why I'm making you that promise right there that again, if you do it right, it will come out as whole numbers or negative whole numbers on your X's, Y's, and Z's. Let's go to number 2 here. Again, as I already mentioned, this is your step 1 equation. You don't have to do any work. So we have to combine the second and third equations so that we can get that same variable, which in this case is y, eliminated. Can't I multiply this one by positive 2 right here? So that this will become negative 2y to combine with 2y. That's exactly what we got right here. I multiplied this third equation by 2, add it to the second equation, and I get, when I add those equations together, 5x plus z equal to 7. So I take the step 1 result that's up here, that it was basically already given to us, and we take 5x plus z equal to 7. We combine those two equations together into step 3. And then we solve that resulting system. Okay, what do we get? Well, if I do elimination again, by multiplying, I'm going to eliminate the z's here. That seems simple enough. X's aren't that bad either to try to do that. But I'm going to multiply, I'll go and multiply the first one here by -1. That gives me negative x minus z equal to -3. Looking at this one, transforms into this. And then you add it to the other equation. The z's cancel, don't they? And we end up with 4x equal to 4. We solve that by dividing out the 4, and you get x is equal to 1. But before you're done with step 3, you got to solve for both variables, don't you? So I go back and I plug it into any equation that has both x and z in it, so I can figure out z. So I plugged in x equal to 1, and I went ahead and picked this one. Seems simple enough. And I get 1 plus z equal to 3. Move over the 1, and we realize that z is equal to 2. So now I have the answer for both x and z. What's still left? What's still left is y, right? That's the one that we still haven't solved for, correct? And so step 4 is where we need to solve for that still unknown variable. Pick any equation you want as long as it has that y in it. Okay. Again, you can't pick the first equation because you can't solve for y if y isn't even in there. Okay. So pick one of these two. I went ahead and picked the second one, the one in the middle. And I plugged in x equal to 1 in there, and I also plugged in y equal to 2 in there. I got this. I then combined like terms. I then added the 1 over to the other side with the other 1 over here. And finally, after you divide out the 2, you get y equal to 1. So therefore, putting all three of those answers together, 1, 1, and 2, I get this answer. Put it in that order, though. That's just like with ordered pairs in 3.1, always put in that order x, y, z. Just like we did x and y in 3.1. Finally, in number 3, some of you may have taken more steps to get this answered. That's okay. If you do the steps right, it'll still come out the same answer in the end, so that's what's important. But I went ahead and multiplied. I decided that I wanted to eliminate the x's right here in second and third equation. It doesn't always have to be first and second or first and third, right? Although you could do that on the next step if the next step is necessary. But it could be any pair you want, okay, as long as it has the two variables. As long as the two equations have the variable in it that you want to eliminate. You can pick any pair you want. Okay, so I want to eliminate the x's. If I multiply by -2, I get this right here. So multiplying it by -2, we get this right here. But then when we add the equations together, what happens? everything cancels, even on the other side it does, okay? Negative 8 plus 8 is 0. And then as we've already said, if all the variables cancel when you combine like terms, that's also 0. But again, what did we say when your result is 0 equal to 0 with no variables? That's a situation where the variables disappeared, but the statement is true because 0 and 0 really are equal to each other. And when you have a 3-variable system, you don't need the fancy brackets that we had back in section 3.1. You don't need to do those, okay? We just have to say what? We just have to say infinite number of solutions when it's a 3-variable system, okay? And so that concludes section 3.3 and chapter 3 in general. And so, as usual, let me know if you have any questions about that. And I really want to encourage you again, okay, once you get these steps down, the big thing is to make sure you just are very careful on your multiplications, your additions, and subtractions. Okay, so you don't end up with one of those weird-looking answers, okay? But yeah, let me know if you have any questions. Have a good day, and we'll see you back for chapter 4.